In this problem, we're asked to find the magnitude of the moment of the 200 Newton force shown in the figure about the x-axis. And we're asked to solve the problem in both scalar and vector. So we'll do the scalar first. And my approach here is going to be to break the 200 Newton force into its x, y, and z components, and then look at the determine the moment produced by each of those components about the x-axis, and then sum those moments to get the moment that the 200 Newton force creates about the x-axis. So I'll start by finding the components of each, the magnitude of each of the components of the 200 Newton force. So the x component is going to equal 200 times the cosine of the x-coordinate direction angle, which is going to give me minus 100 newtons. And that means that we have the x component acting along the negative x-axis with a magnitude of 100 newtons. The y component is 200 times cosine 60 degrees equals 100 newtons. So the y component acts along the positive y-axis, and f sub z equals 200 times cosine 45, which equals 141.4 newtons. So it acts, f sub z acts along the positive z-axis, and its magnitude is 141.4. And I didn't write down the magnitude of the y component there. Okay, so now I'm going to determine the moment produced by each component about the x-axis. And before I do that, we need to realize that a force that is parallel to an axis or has a line of action that passes through any point on the axis does not produce any moment about that axis. So I'm going to repeat that because this is very important to understand. A force that is parallel to an axis or has a line of action that passes through any point on the axis does not produce any moment about that axis. Now we're going to use that in our first, looking at the first component, f sub x. F sub x, by definition, acts parallel to the x-axis. Its line of action is parallel to the x-axis. So therefore, it does not produce any moment about the x-axis. So we don't have to worry about f sub x. F sub y is 100 newtons along the positive y-axis, and the moment of f sub y about the x-axis is going to be the perpendicular distance between f sub y and the x-axis. So let me extend the line of action of f sub y, and we can see that the perpendicular distance from the axis to the line of action of F sub y is going to be 0.25 meters. So let's start writing our moment equation here. So the moment about x is going to equal F sub y times 0.25. Now we need to worry about signs here. And generally we assume counterclockwise moments as positive. So let's look at the direction of the moment created by F sub y. F sub y is above the x-axis, and its line of its direction, its sense, is going to the right. So that is going to create a clockwise moment. So we need to put a negative sign there. Okay. Takes care of F sub y. Now F sub z, its moment about the x-axis, let's extend its line of action so we can see the perpendicular distance. We can see the perpendicular distance is this distance here, which is 0.3 meters. So the moment of F sub z about the x-axis is 141.4 times 0.3. Now we need to determine, is that a clockwise or a counterclockwise moment? And we look at it and see that F sub zx to the right of the x-axis, it's going up. So it's going to create a counterclockwise moment, which is positive for based on our assumption or setting counterclockwise moments about the x-axis to be positive. So we do that math and we get m sub x as to be 17.4 Newton meters, and that's positive, so that indicates that it's a counterclockwise moment about x. Now let's look at the vector analysis. So for our vector analysis, we're going to use what we also talked about in the lecture, that we can calculate the moment of a force about an axis by using this equation, where that moment is equal to the a unit vector along the axis dotted into the moment of the force about any point along the axis. The moment about a point is r cross f, and we can write that as the determinant of the magnitudes of the components of the unit vector the magnitudes of the components of the position vector and the magnitudes of the components of the force. Okay, so in our case, we want to find the moment about the x-axis. So we're going to need a unit vector along the x-axis. That's going to be simple. We need a position vector from any point on the x-axis to the force. And in this problem, the convenient position vector is going to be from O to A. So I'll write that here. And that will be crossed into F, which is given. And we already have the components of that from the scalar analysis. Okay, so let's express everything now in Cartesian. So the unit vector along the x-axis is simply I. R from O to A is going to be 0I, because there's no change in x from O to A. The change in y is a positive 0.3 meters. So let me write that, 0.3 J. And the change in z is a positive 0.25 meters. So let me write that. And I might have said, I'm not sure if I said J. I should have said K there, the change in Z or K. So R from O to A is 0.3 J plus 0.25 K. And then the force is simply the magnitudes of the force that we calculated earlier associated with their respective unit vectors. Okay, so we're going to set that up in a determinant where our unit vector components are simply 1, 0, and 0. Our position vector components are 0, 0.3, and 0.25. And the components of the force are negative 100, 100, and 141.4. So to calculate the value of that determinant, I'm going to cross out the first row and first column. And I'll do the math out here. The first calculation is going to be 1 times the quantity 0.3 times 141.4 minus 0.25 times 100. And that's going to be it, because the J and K values of the unit vector are 0. So there's no more math to do from the determinant. And now I do this math and get 17.4 Newton meters. And since that's positive, that indicates a counterclockwise moment about the x-axis, which is consistent with what I got in the scalar analysis. Now notice the similarities between the vector analysis and scalar analysis. You know, it's just how you slice the problem. Look here. There's that moment of the 100 Newton force about the x-axis. Here's the moment of the 141.4 Newton force, the z component about the x-axis. And notice that the negative 100 newtons, the force in the direction of the x-axis, the x component of the force, which is the component in the direction of the x-axis of the force, had nothing to do with the moment of the overall force about the x-axis.